All right, thanks for the invitation, everyone, and big thanks to Rachel for organising. So I'm going to talk to you about Molly, which is molecular dynamics package in Julia. It's kind of approaching 6 years old or so now. The outline is spend about 25 minutes or so kind of outlining the package, talking about what it does, why, and then the rest of the time will be more hands-on exercises. You guys doing some stuff in notebooks. You can find the exercise notebook now if you want to have a look or start setting it up. It's on the GitHub, so here's the Molly GitHub page. You should be able to search for that under exercises. It's there, so you'll need the notebook file and 2 data files. If you installed Julia 1.11 yesterday, that's fine, it should work fine. The notebook was tested on 1.10 as well. And then periodically go through some answers to the questions. I probably don't need to introduce this too much to this audience. Molecular dynamics, you basically set up a physical system, so that's atoms in some orientation. You define the rules that determine how the atoms interact, and then you basically press play, which in practical terms means numerical integration of F equals ma. There's not really any shortcuts unless you want to do kind of enhanced sampling stuff, so this is often very computationally expensive. On the right here you can see a small peptide, small protein kind of flopping around in water. That's just a few picoseconds, I think, of interaction. And MD has helped us understand many processes. It's worked particularly well when it's kind of used in collaboration with experimental results. And as we go forwards, we've got more and more compute. We've got all these crazy and amazing machine learning approaches, and we have AlphaFold, so great approach to structure prediction, give us starting structures. So these methods. So as an example, here's this isn't my work. This is from John Coder's group. You can simulate this protein, and the simulation time's on the bottom. So this was a fairly long simulation, approaching a millisecond. And from this, you could, for example, form a Markov state model, which shows the transitions between different conformations, and you can obtain transition times. Another example from D-Shore Research. They made this simulation available of SARS-CoV-2 spike glycoprotein. So you see the protein in kind of red, grey, and cyan, and then the glycosylation groups, so the sugar groups, in orange, top round. So there have been some successes in the field, particularly folding small, fast-folding proteins. In this paper here, they managed to get the correct structure of these small proteins. Good for interpreting mechanisms. You can get information which is hard to access with experiments. So atomic level resolution, basically. And in the last few years, we're starting to see binding free energy methods become more and more popular in the pharmaceutical industry. To kind of develop and improve some molecule binders, and it's now a routine part of them. However, the Cas protein structure prediction assessment, MD has kind of consistently failed to predict the structure of proteins. Disorder proteins, in many force fields, they're too compact. So, for instance, on the right, this isn't a disorder protein, but you can see how the behavior is different for different force fields. And if you want to do enzymatic reactions, that's a problem. You need to do something like QMM or use a machine learning potential with your molecular mechanics model, because bonds can't break. And really the key concern that should be in the forefront of your mind when using these methods is the question of interest. Can it be answered on the timescale available for study? Okay. The brutal fact is often it just can't, because many things happen on the scale of seconds or milliseconds even, and and we just can't reach that simulation time. That said, there have been some promising recent developments. So we have Moore's law, so it's still holding in GPU space. So the available simulation is going up and up. Software is getting better and better. Force fields are improving, and in some cases can now work well on disordered proteins. Yeah, I've already mentioned the free energy perturbation methods and AlphaFold. So probably the biggest development has been machine learning potentials. So there's been a lot of work recently to show that neural networks can give kind of DFT level accuracy, quantum level accuracy at much faster speeds. And these methods they're trained to match forces and energies on quantum data sets. They can show issues on longer simulations, but that has been addressed in the last year or two. And the field is addressing problems like how to deal with long-range interactions, which are important in biological systems because they will take place in water, and the kind of the performance compared to. So these are very promising, but aside from a few kind of specific studies, for instance, this big one from Google, they're not immediately applicable to biological systems because they're just too slow. So, okay, what's the software landscape for electric simulation? Well, there's a number of amazing, really mature software packages for MD. Shown on the right, for instance, you have GROMACS, NAMD, LAMPS, OpenMM, etc. There's a few more, and usually they consist of fast kernels under the hood, which will be written in C, C++, CUDA, whatever, and then some layer on top with which you interact. So, for instance, GROMACS has binaries, OpenMM has a Python interface. And so most packages are kind of hard to interact with all the way down and hard to kind of customize. And no mature package has support for differentiable simulations, which I'll describe later. So Molly it's a pure Julia implementation of electrodynamics. It's one language all the way down, so everything in there is Julia. Simulation scripts are just Julia scripts. So in terms of design, it's kind of closest to OpenMM, which, as I mentioned, has a Python API on top of multiple different kernels. And there's kind of an analogy with the Julia base language. In Julia, a lot of the standard library is written in Julia itself, and the reason that's possible is because Julia is fast. And so here we have the same principle. If the user defines a potential, a simulator, or something, it should be just as fast as the ones which are in the actual package. And so we can simulate proteins, and the trajectories match existing software. So on the right, for instance, you see this protein flopping around. This is simulating fully. It's differentiable, so you can take gradients through simulations, and the gradients are accurate with respect to. So just a really quick whirlwind tour of some of the features. We have standard non-bonded interactions and bonded interactions. You can set up from GROMACS standard topology and structure files. We implement the Atom base interface, which you've already been introduced to, and the Atom calculators. We have some various kind of simulators like Longevin integrators, minimization, various thermostats and barostats, periodic boundary conditions. We have a nice logger interface, so that allows you to track properties throughout the simulation. And yeah, we're also compatible with Unitful, which has been mentioned. You'll see some more of that in the exercise. That's actually nice because it removes whole classes of errors. Well, you still see them, but they're not silent errors. It turns a whole lot of silent errors into loud errors, and that's a good thing. It has some analysis functions and some visualization functions. What it's lacking is there is only partial support for constrained bonds and angles, so that's ongoing. Ongoing work on particle mesh yield summation for long-range charges. And a few other things, particularly kind of high performance, and I'll come on to a bit later about why that is. So to summarize the pros and cons, easy to add new features, hopefully fairly easy to understand because language barriers halfway down. And the differentiable simulations are fast. Disadvantages kind of lacks a bit of maturity testing and features of the really mature software. and the GPU multi-threaded performance is a bit below that of software which is specified to specific interaction types. So just to show some kind of overall code, you can kind of set up components individually. So we import the package, we define a cubic boundary. So this means we want a 2 nanometer box, which you can see on the right, 3D. You can also do 2D. We set up the temperature, then we define some atoms. We use the place atoms function, which just puts them randomly in space where they're not clashing. We generate random velocities for the Maxwell-Boltzmann distribution. We're going to use a Leonard-Jones interaction. Yeah, I mean, most of you probably know what it is, but it repels at short range and attracts at long range. And then a simple velocity Verlet integrator. We set up the system, and we call it simulate function. And this idea of setting up a system with a system call and then calling simulate is kind of the standard way to do it in Molly, and you'll see that fairly consistently. And then we do have some basic visualizations, so you call this visualize function, which produces the animation. So you've seen that before. The animation is not in Molly, the animation's in IMOL, but the simulation itself is generated with this code. So in this case, you're loading in a force field. So this is all the parameters of electromagnetic force field. You then set up the system from the force field and the structure file. We give it some loggers to log properties. We then do a minimization before we generate the velocities. And then we use the Langevin integrator, which kind of adds noise every step. In this case, we're also using the Monte Carlo barostat, which is a way of keeping the pressure constant, so it changes the box size. So in this case, we're running an MPT ensemble because we're keeping pressure and temperature constant. And again, we run simulate. So there's 3 types of interaction, Molly. You can have pairwise interaction. So that's, for instance, a Leonard-Jones potential, where you want every pair in the system, or perhaps most pairs, you can do exclusions as well, to interact. And here I've given the example of the Mio potential, which is a more generalized version of Leonard-Jones. You have what's called specific interactions. So let's say you're simulating some water in electromechanics. You would define each hydrogen to be bonded to its appropriate oxygen. So that's a specific interaction between those 2 atoms. And then we have the most general type, for which we use basically the atom calculators interface, where we just say, give a function all the coordinates and get back the forces. So we could use that to call DFT or to call potential. So if you wanted to find a custom interaction, that should be fairly easy, as I said. So for a pairwise interaction, you just need to subtype this abstract type. You then need to decide whether you use the neighbor list. And then you define, as a minimum, if you want to do a simulation, you define the force function. And you can also define a potential energy function as well. And there is a PR open to change this interface a bit. So currently on GPU, the force summation kernel is really very simple, stupidly simple. Each thread just calculates the force for one neighboring pair. Actually, performance, although it's not great, it's not atrocious. It's like 5 times slower than OpenMM for fairly small systems. Without kind of too much optimization on our part. From the user perspective, the key point is that the interaction function, so that's the one I showed on the previous slide, this force function here, this is the same whether you decide to run it on CPU or GPU. Enzyme, which is this great package for automatic differentiation, is, to my knowledge, the only way to differentiate through CUDA kernels like this, and it works nicely. Well, most of the time. So let's say you have some bulk water. This system on the right is about 3,000 atoms. Single-threaded CPU is about 80 milliseconds per step, going all the way down to GPU, about 300 microseconds a step, or about 4 times slower than OpenMM. As the system gets bigger, our scaling is poorer, so we're more like 20 times slower. Again, this is on the development branch. Unit 4 units don't slow things down too much. There was some discussion before about when to remove units, can they go all the way down? We keep units most of the way down, and then right at the very lowest level, we strip them off for speed reasons. So on CPU, hopefully single instruction, multiple data, SIMD, should allow us to close this gap. However, you do run into tension here. The tension is between flexibility on the one hand, which we want to keep, and then really specializing the memory layout on the other hand. So on GPU, there's some work ongoing to use kind of clever neighbor ordering and reductions, which should give us quite a big speed up. Like being realistic, we're not going to reach the speed of kind of lamps, Chromats, etc. However, we can certainly aim to be the fastest for small to medium systems when you're using custom interactions. That's very achievable. And then if we want to think about scaling to really large systems, you have to think about kind of splitting up your system into domains. That's not something we're currently thinking about, but maybe one day. So I mentioned differentiable simulation, so I'll just outline that briefly. So it's probably easiest to describe in relation to recurrent neural network for those who are familiar with that. So let's imagine you have an RNN which is looking at a sentence of words, and it's deciding whether this is a happy or a sad sentence. And so your network kind of goes along each token or each word or whatever, each letter, and it updates its internal hidden state. And then at the end, it's got some output, which you then compare to the true output. And you obtain some loss value. And then because you've implemented this in a automatic differentiation framework like PyTorch, TensorFlow, or Julia like Enzyme or Zygot, you can call dot backward, and you can obtain basically the gradient of the loss with respect to all the parameters in your system, which in this case will be the neural network weights. And so for a differentiable simulation, kind of a similar idea. You have a starting coordinates in your simulation. You run a simulation according to Newton's equations of motion using your force field. You then get some loss value. So in this case, I'm just saying the root mean square deviation between the final coordinates and the experimental coordinates. And because, again, you've been clever, you've implemented this in an AD framework, you can call backwards, and you can obtain the gradients of that loss with respect to all your force field parameters. And so this lets you update your force fields to better match experiments. And so in this work we kind of started off with these flat potentials, and we basically learned to match potentials for a protein that corresponded to potentials in the protein data bank. And the appeal here is the kind of variety of loss functions. But almost any property you can compute from the structure over time is available. So you can train your force fields to kind of have whatever radius of duration you want, or maybe to have a certain rate of distribution function, certain phase change, or fit to some kind of electron microscopy data. So I said there was no really mature software for differentiable simulations. I think that's a fair statement. There are some really cool packages. There's JAX-MD, which is probably the most used in JAX, obviously. There's TorchMD, PyTorch. There's a couple of others, but they're all promising, but they're all limited in some way by scope or performance. So JAX doesn't really have proteins. TorchMD is a bit slow. And so we do differentiable simulations. On the release version, we use this kind of Frankenstein mix of Zygot and Enzyme so Enzyme's used for the slow bits because it's faster, and it's all glued together with Zygot. On the development branch, it's Enzyme all the way through. And if you want to read more about how that's used to do science, then we kind of use this to improve implicit solvent force field. So in implicit solvent, you basically take all the water out of the system, and you replace it with this kind of infinite medium that mimics the water. And so we use Molly to modify an existing force field and an implicit solvent model so that its performance on disorder proteins better matches experiment. So there's kind of ongoing work in Molly across the board. We just updated to Atom Space 0.4, so that's in the latest release which came out last week. And I mentioned the switch from zygote to enzyme, which, I mean, the reason we did that was basically because zygote doesn't allow you to do mutation. And if you want to write fast code, you have to use mutation. And so enzyme is more compatible with faster code, basically. And you can check that on the no-alloc branch if you want. My PhD student, Giuseppe Gambini, is working on faster simulations on GPU right now. There's also work going on switching to kernel abstractions, so it works on all backends, work on UL summation, constraints. And the API is kind of still changing a bit. But once everything's sorted out, there'll be a software paper. Okay, so just kind of a grab bag of different simulations. You've already seen the peptide simulation. Diatomic gas, you can imagine the hydrogen molecules flying around. Here's the solar system, so Rachel actually used that example earlier. You can simulate anything because ultimately it's all just physical systems. So if you're using Unit 4, you can just, instead of using a nanometer, you can use a million meters, that's fine, it's not a problem. You can make or break bonds. That's still, I mean, it works, it's a little bit hacky, but it does work. And it's just quite a nice interface to play with different potentials and implement. So if this is interesting to you, there is a fully funded PhD position being advertised right now on the LMB website, working on machine learning potentials and kind of this stuff as well. And there'll be an advert soon for a postdoc position on improving molecular mechanics force fields. And that will include working on Molly as well, so do chat to me if interested. So I'll do the acknowledgements now before the exercises. So thanks to the many Molly contributors and to all Julia contributors and faculty authors, to the Julie Wilson community, many of whom are here, William Moses and Valentin Jaravi for Enzyme, who have helped with a lot of stuff, and everyone at GROMAX for kind of, because we copied all their stuff. Okay, so I'll just introduce the exercises, and then we can do any questions, and then we can get on with the exercises. So they can be found on the Molly GitHub. You'll need the exercise notebook and the data files. Julia 1% or 1.11 should both be fine, not a problem. Ideally use Molly 0.21 though. So we'll go through some answers at kind of intervals. So there's about an hour and a half left. So probably do three sets of kind of answers every half an hour or so. Just go through some. And as you work through, you may need to refer to the Molly documentation, the link of which is the notebook. I'll obviously be walking around. There's also some people who've used Molly in the room, so Tina's who's there, for instance, and I think Rachel's used it as well, so do feel free to ask those as well. Yeah, okay, so that will conclude the talk part, so I guess any questions at this point? Rachel.
For the differentiability when you're training the force fields, are you actually differentiating through every single step of the trajectory, or is there some like clever, you are, okay.
We are, and the clever trick is using gradient checkpointing.
Mm-hmm. Oh, sure, okay.
Because if you don't use checkpointing, then the memory requirement is linear in steps.
Yeah, that seemed like it would get painful.
I say thankfully, this is also a problem with recurrent neural networks.
Right.
So thankfully there's been a lot of work.
Gotcha.
You basically, with gradient checkpointing, you just store intermediate values. So you basically turn the memory requirement into a recomputation requirement.
Gotcha.
You store intermediate values, you then have to
reconstitute it later, basically, to fully propagate.
You could, in theory, store it all on disk as well if you wanted to.
Sure.
In the extreme thing, yeah.
OpenMM, when they kind of sum all the forces together in parallel, I think they convert it to like 64-bit integers. Is that something that's possible with Enzyme?
Yeah, this is so. Yeah, just to outline the reason why they do that. So when you're adding big numbers to small numbers, that's a risk in low precision, and so for certain accumulator values like accumulated energies or forces, virials particularly, MD software would often use high precision. So currently in Molly you can use any precision. It will be the same precision throughout. So longer term, a nice feature might be to allow a different precision for the accumulator values. In Enzyme, that's fine, it works. You just need to specify the type. So as long as Enzyme sees it in the type domain, so it sees it at compile time, then type conversions will be fine.
Okay. I think with using integers, I think it's also like more deterministic.
Yeah.
With floating points, I guess.
Yeah. So Enzyme basically doesn't really do anything with it. It converts them to floats for gradient purposes, I think, because a gradient with respect to an integer will be 0 everywhere, basically. So it just converts it to float. So we don't use ints anywhere basically for kind of things that are integrated, such as just flows throughout.
This is super cool. So thank you very, very much. On slide 21, when you talked about the comparisons against OpenMM, what level of accuracy or approximation is this? Apples to apples on both sides, or is this with EWALT summation on one side and
that's a good question. So this is so it's apples to apples, but it's with reaction field, not UOLT.
Okay.
And we just try to remember the exact details here. So we haven't implemented full constraint support yet as well. But I believe this comparison was done without that. So yeah, it's apples to apples, but we don't use PME, we use reaction field.
Thank you.
And the reason it's 4 times. 4 times is quite an impressive number, because it's a small system. But when you get to actual larger systems, it's more like 20 times.
Is that because, are they already doing like domain decomposition at that scale, or what's the thing that changes?
Honestly, it's because they don't really care about small systems, because OpenMM is basically for simulating biomolecules. So if you wanted to cram the only biomolecule you could cram into there would be this peptide, which isn't very interesting. We've got to start somewhere.
Another question. So that list of potential loss functions that you showed seemed, in most cases, quite heavily focused on matters of structure, which of course is very relevant to biomolecular stuff. I presume that most dynamical properties could also fit totally fine within this framework.
Yeah, they can. Actually, having done more research on the area, I think actually the unique case for differentiable simulation is the dynamical properties, because there's something called trajectory reweighting methods like force balance that could already fit to a lot of these. So I've got a paper coming out hopefully by the end of the year comparing trajectory reweighting to differentiable simulation. And the takeaway from that is that the gradients are really surprisingly similar, like really amazingly similar, even though one involves differentiating the Boltzmann equation and one involves differentiating an MD simulation. The gradients correlate very strongly. But the one thing that the trajectory reweighting can't do, because it differentiates the Boltzmann equation, is dynamical properties. Because in the Boltzmann equation, you can just switch all the states, switch all the order.
So there's no timescales.
No timescales. Yeah, it's all just snapshots. Whereas when you're differentiating through simulation, you can fix a dynamical property. So for instance, in this upcoming paper, we fit to diffusion constants.
Quick one. Can we do MV calculations?
Do what, sorry?
The macro-canonical ensemble.
So so micro-canonical is just with no thermostat. So you just don't specify anything. So So actually, in this case, we use an thermostat, so this is MVT. But if you commented out this line, it would go from canonical to microcanonical on top. Any other questions?
A little bit off the beaten path, the solar system example that you showed,
Yeah.
what is the integrator there? That sort of n-body simulation problem?
Yeah.
That's probably not perfect.
Given that it's just an example, and I don't know anything about this system, I probably used the wrong one. I used Verlet, yeah. But you can implement a different one. I can show you the Verlet code if you want. It's not too.
It's kind of remarkable that it looks that way, given the low order of accuracy. But
I mean, I used a very low time step, and it's not a very long simulation. I just changed the parameters to make it look good, basically. I'm 100% sure it's not a good astrophysical simulation. But it is just basically things orbiting, so yeah, hopefully, yeah. It'll probably diverge after like 10 more orbits.
sure, that's cool.
Let's show you an example of the Verlet code. So here's the struct. So you need the time step. So you need the time step. You can have an optional coupling. And this just gives you the option to remove the center of mass motion, bit of technicality. And then in the simulate, you do some kind of setup, and then every step, you calculate the forces, you get the accelerations from F equals ma, and then in Verlet, you basically update the velocities, so that's this line, and then you update the positions, which is this line, and then most of the rest of the code is just complexities around constraints. So a constraint, for those who don't know, is, let's say you have a bond and you don't want it to vibrate, you just want it to stay fixed. So every time step, when it diverges, you just move it back. And so there's just some complexities around keeping that. But otherwise, this for instance, is the whole Verlet loop. And then the Langevin loop is kind of similar. Forces, F equals ma to get accelerations. Update the velocities, and then in Langevin you add random noise, so you generate noise here, that's the velocities. And then I'm just thinking if there's anything interesting else to show. Nothing's really jumping out, I think. That's probably the main interesting bits. Okay, any questions at this point? Right, so get going on these exercises. I'll kind of be walking around, and then maybe in 20 minutes or so, 25 minutes, we'll review the first few answers. And yeah, that's pretty much it. If you kind of can't be bothered to do the exercises, that's fine. Just read the documentation as well, and I'd be interested in any feedback. So, yeah.
And if anyone has trouble just like getting the notebook spun up in their environment or anything like that, or installing packages, maybe we can do again like we did yesterday, like quick raise of hands if you're just like pretty comfortable in Julia and could help with that kind of thing, so people know who they can look to. All right, so yeah, there's a few folks around the room if you have trouble just like getting things up and running, who may or may not know Molly themselves, but can probably help you just get things installed and to the point where you can run the code. So let us know. Quite a bit longer than DMTK, which is interesting.
I'm not sure.
You already set it for
Yeah.
So just remove the second.
Yeah, it's fairly talkative while it's installing stuff.
Yeah. Oh, yeah. This is the second unit. Yeah, so just do there. Then if you just connect those.
Exercise.
Yeah, just got those low because it's separate spaces. Not the logos. So if you just have to separate it by one space.
I missed this earlier, but why was the speed of the microphone?
Oh no, so it was relative to OpenML.
Okay.
So it was, yeah, so
I see.
OpenML has clever
I see.
parallelization, whereas I just use stupid thread stop, threading or whatever.
So in theory, that's something that could.
It is. My own interest is purely GPU because almost everyone uses GPU for my remote. Because you get like 100, you get 100.
And you're closer.
Just fix.
Actually, I think it's even worse than that because OpenML is slower than GrowMax, so it's actually another factor. Basically, at the minute we don't use SIMD at all. That's the single thread difference. And then on top of that, we don't use feather reduction. But if you're running on 16 threads, you make 16 copies of the forces. But yeah.
No, but the new neighbor list should fix it. Because it's made just made to fix these things.
Yeah, that's what we want.
So, get into it. What visualizer does this open up?
Okay, then you have then
3D Model.js.
Uh,
Yeah, 3D Model.js, which is really nice. It literally just wraps the JavaScript.
yeah.
So actually, if you look at your save notebook file,
Oh, yeah.
massive load of JavaScript into it.
Can you do any distributed?
Not Chrome.
If that's something you care about, maybe more.
Not really. You mean like using API types?
Yeah, like
We might carry on to GPU, but we're focused mainly on GPU, so we probably wouldn't put the effort to do like.
But I mean, even if you have 3 GPUs on one rack,
Not currently. Yeah. So could on data.jl is maybe a little bit lacking. It's the ability to easily use. I think there's a package called one of the array packages. Arrays or like basically, if you have a large array, it's like a third of it. And then when you do a broadcast, separate the rest.
Can just download.
Yeah, so there might be a way to do that. But I guess that's only when the saturation size-wise, so it's yeah, yeah. Yeah, it is.
Well,
Yeah, probably the boundary is like,
About 2,000.
no, like the overhead is just.
Yeah, I guess human communication.
Yeah. I haven't actually heard of this, but that's so the other factor is that you have to balance, for a small system, you have to balance the ability to do embarrassing parallel work, right?
Yeah.
So if you have 4 GPUs, in that case, you would always do 4 separate simulations. There may come a point with very large systems where it's better to use all 4 to do one simulation. No, you would, yeah. I mean, it's just, like, that would be like a small protein. But if you wanted to do like so something you might just look at ribosome proteins, the ribosome is a huge complex with loads of protein, loads of RNA, and that would be
Sorry to see. So it would be crystallized.
I went to biomedical use so many
yeah,
does.
well, grow maps to
Create
that's right. Those are probably the big things.
Why not? Because I added the assignment of the energy in the old cell after I'd already run the minimization.
Where's that link?
Yeah, that's the way
I've done something.
Probably grow maps is the most useful one.
Oh, look, now it's a negative number. Excellent.
And there's also the amplitude. Another factor of the sample.
even still.
Maybe it's
Need raw performance.
I know they're thinking about machine.
Yeah.
Problem is, like, if you're hyper optimizing for one,
Yeah.
no point in spending anything like it.
Yeah. Well, I think it's like people. This is why I'm surprised that they still have that way. Because a lot of their MS stuff suffers. Graphics cards are pretty well optimized for that already. So.
Yeah.
Lesson you are already in a lesson.
Sometimes not to study. But not really sort of allergy type peptides. Low system, yeah.
My website, City.
Just RM.
This was all okay.
That's like just
Comparison. What's the end? It's like a. Yeah, so this is for two different loss values.
I don't know why I switched.
This is with see how fine versions.
Yeah.
It's of course the same.
Right, right, right.
No, it's not. It's in the infinite limit. It should be able to. By infinite limit, I mean the limit of the sum.
And then the two years. One
The reason is
exercise
that,
two exercises.
yeah, so also making some.
Okay, you are here. Tell me. Steep this descent.
That's a whole thing, but the stat max says nothing about what.
Basically, they're not. It's practice. I find people trying to make it up 200 steps. That flow as well.
It's gotta be on that.
You can actually show explosives. So in this work, basically, what I do is no longer classification. What I do is spawn it with the grid, and you get this equation that grows every step. And the first term of that equation. So the gradients explode basically necessarily. The reason is because every step you take, every previous step is contributed. Okay. So you're kind of exploding in that sense.
Okay.
And so we truncate off like two. If you go to 500, 1,000 steps, it's explode. So by truncate, I mean you only step. So if you're doing like a snapshots to the gradient of 1,000 steps, so you've got 1,000 snapshots, and you're comparing that to when you use those thousand factors. As you go through the simulation. So that's also good for speed as well.
Right, that makes sense. At this point, how much of a leap is it to write additional integrators? And in particular, if one wanted to put in an integration scheme also. You would differentiate through that. That's I would certainly help with a lot of challenges that you there's a whole not one conscious root, many conscious roots that are just all about arguing about parametric forms and the specific parameters of memory kernels or various sticky technologies. So that dynamics.
Oh, no, I possibly, I don't really use it. The principle of everything's
This is running from the master.
very individual operations.
I guess
Yeah. So the challenge is basically that to get your next position velocities, you don't just look back at your position velocities, but watch the steps that might be.
That's okay, yeah, that's fine. So that would work in automatic machine.
So that's all initialized.
In this scheme, we're actually providing you to rederive
Run it.
these grades, basically.
Okay. I saw that there was a set of slides from Leonard-Jones at Bristol.
There's one in Cambridge.
Yes.
I see.
Yeah.
Did Leonard-Jones have something to do with Cambridge?
Oh. Yeah, good question. It started out maybe like 2 years ago.
That's really cool.
Yeah. Now if you have.
Chuck was involved in all
That's awesome.
that. Yeah.
Have you met Ethan in person?
No, oh, he's there. Nice to finally meet you.
That's my advisor.
Yeah, yeah. How are you? Yeah, yeah.
I missed the first one.
Yeah. Oh, that's good.
I've been trying to
Yeah.
send you use Julia.
Yeah.
It's the first time.
Yeah, if you don't mind, how many years?
Yeah, of course. And there's a break after this, right?
Yeah, yeah, yeah. How did
One
you-
tricky one that gets plane damage instead of.
Right, yeah.
Remind me which years he was at Bristol. It's like 7 or 8 or 13. Low, it's definitely less than 20 years.
Yeah, yeah, yeah.
It says on
Yeah.
Oh, you got it.
25 to 32.
25 to 32. Yeah. So it is tradition at the University of Bristol, and it's this classic like tradition
Yeah.
that
Well, when
anytime you show a picture of somebody who's from Bristol, you are always supposed to put their name and then parenthetically afterwards the years that they were at Bristol.
It looks like he died at age 7.
So it, so the very first time I saw this, I'm like, surely that's a typo. 1821 to 1832. Yeah, it looked like he died as a little kid. I'm like, wow, tragic, very, very short, tragic short life, but did a lot in those 7 years he was on the planet Earth.
Yeah, that's all.
Extra context.
Right. Did
With
that,
like her and one other student were just like, hey, can you like do it here? And he was like, yeah, we can. And then they asked Julia people and they're like,
Yeah.
okay.
You're organizing jury.
I am the co-chair of the local committee. So yes, I am involved. I'm excited, it should be cool.
Yeah, yeah.
It's gonna be,
That much work.
gonna be crazy. Yeah, no, so far it's been chill. I think right now we're still sort of, my hope is that we'll be able to, because we're not certain yet about exactly the venue, like,
okay.
and it might be some split, like maybe the workshops are at CMU and the main conference is at Pitt, and then the hackathon is at CMU, or something to that effect. And basically, my hope is that we'll be able to play their conference services people off of each other to give us a cheap deal. So I'm waiting, Alessandro got like an informal quote, but I'm waiting for him to get like a spreadsheet one like the CMU people gave me. And then, so Pitt's quote right now is quite a bit better than CMU's, and so the hope is that we'll be able to go to Pitt and say, hey, here, because I think they should both be interested in drawing a really large conference, like, the university should be interested in this. Pitt is quite a bit bigger, yeah,
But our CS school has that.
that's also true. So yeah, we're hoping they're very, it's been interesting getting involved with the local committee. They're very committed to trying to keep costs down because they know so many students come and they wanna keep the student rate affordable. So we're thinking about all kinds of creative stuff, like, unlike in Eindhoven, there's a lot of inexpensive restaurants around here that are walkable, so they're thinking about maybe catering less stuff and then seeing if we can do some kind of like coupon or discount deal for conference attendees, and that can help keep ticket costs down.
So is it in the spirit of
So we're exploring all this kind of stuff right now, but a lot of the specifics are not yet set in stone. I think once they are, then there'll probably be a lot more like on the ground work related to some of that stuff. I think that's where their local committee really comes in, is like, if you have to literally like walk over to a hotel and like bang on somebody's door to figure out like a room block or, stuff like that. That's, I think that's a lot of where we'll come in. But a lot of the centralized stuff is all handled by the global committee. Like, in principle, none of us, if we choose to volunteer where we can, but like program stuff, like the CFP, all of that, like that's all handled centrally by the global committee. So it's really like the local part is really just like the local stuff, which is nice.
Well, that's out loud. I saw the ad. I was like,
Yeah, I'm impressed.
Yeah, they pitched me on it increasingly aggressively, and I was initially quite nervous. I've been running like a user group in the area, but I really wasn't sure like what the level of enthusiasm would be, because you obviously need to be able to recruit a lot of volunteers.
Well, that's what they're saying, isn't it? They want people to do user groups first to show that.
Right, well, and so my initial response was like potentially interested in it, but like it seems like it would make sense to run like a local first. Then I think what happened was they probably didn't have too many credible options for the next global, and so they kind of pushed on me. Yeah, exactly. So they kind of started pushing on me a little bit, and so I pitched it to the local group, and people were like, almost everyone was like super enthusiastic, like, yeah, this sounds great, like we're down to help out. So then I was like, okay, maybe this is not like entirely insane.
there's plenty of people here who use Julia and just don't come to that
I know.
either.
I know. Yeah, I'm definitely gonna make an announcement at some point to tell people they should add themselves to the email list for the local group and get on the Slack channel and stuff, because large number of the attendees here are local. I think it's like roughly probably 2/3, 1/3 of the in-person attendees are like local versus came from town. So hopefully if we get some people like Abhishek here catching the bug, you're gonna start coming to our user group.
He is my point of contact.
There you go.
Step one is uninstall Map.
No. You won't.
Oh yeah, that's useful.
I also get plenty of encouragement to
First person
use Julia for my job.
.jl.
Despite the fact that I've been a Julia user for longer, teeny tiny bit of that I'm involved in, like with my name and nothing else. Because I took classes long before it really, I had all of those. I think the vision, people who were far smarter than I had this long-term vision.
There's all sorts of
I
random
did not.
stuff.
Tons of PhD students just don't even understand the vision.
Not
So I just
a
plotted
layered
my way
structure,
into some homework and final projects for class, the grading scheme, class was.
Right, okay, so let's review a few answers, see where we get to. So hopefully everyone installed and got going. If you didn't install and got going and you still want to, then just grab me afterwards and I'll help you. Okay, so you can open up this dipeptide, which is two alanine amino acids together, so it's the building block of a protein. And similarly, you can see it kind of atoms. Okay, so exercise one, why do we need to use so much water? We've got if we zoom in, we've got quite a big distance to the edge. Why can't we just pack it in really tightly with water? Any ideas? Yeah?
Actually, I had a question about, once we load the system file, how do we tell which atoms are part of the water versus the peptide?
So there is a atoms data field to system. Atoms data includes the element of each thing and the atom name. There's also a topology field to system. So topology means bonds basically, and so you can have a look at that as well. That kind of defines a graph-like structure.
And so are all those kind of like immutable, like after you make the system, you shouldn't like be changing those?
Actually, you can. There is an example in the docs where we break the bonds, but this is a little bit hacky and it's not thoroughly tested. But you can add and remove specific fractions. So that you could think about implementing a reactive force field like that. In reality, reactive force fields are a bit different. And then of course, machine learning and DFT don't use the concept of a specific bond at all. They just kind of use the concept.
Sorry, follow-up. How about adding and removing particles?
Okay, that's hard at the minute. That you basically can't do. There's an issue open on that. Yeah, it would work for very simple things.
That ruins my dream of when.
Well, so there is a hack you can do. You might wince at this basically, but you basically use dummy particles on the end, right? That when they're not initialized, you don't care where they are, and then you kind of initialize them, then you do care where they are. And you'd have to deal with that administration yourself of resetting those particles to the point where you want them to be when they get turned on. Ghost particle, yeah. And that would put a limit on the maximum number of particles you had. Yeah. So again, grand canonical, we'd like to do it, but it's a balance of flexibility against speed, right? Because a lot of speed things are just easier if you assume kind of fixed. Okay, any ideas about why you have to have a lot of water? So what happens when...
Just to clarify, the question is just like basically how big, like the fact that you have this big box with all this extra water when the molecule you're interested in is sort of just a small
Exactly,
piece in the middle there.
Yeah, and this is a periodic box, so when an atom goes out one side, it comes in the other.
So presumably there'd be some sort of interactions with that molecule and its own periodic images, right?
So there is another dipeptide molecule in the periodic boundary in the next periodic box here. You don't want it to communicate with itself, because if it communicates with itself, then you're not simulating the thing you think you're simulating. Because what you want to simulate here is just one molecule. So typically, if you have a cutoff radius in molecular dynamics, let's say you have a 1 nanometer cutoff, you would want the distance to certainly the distance from the molecule to its next image to be greater than 1 nanometer. Okay, so then we load and set up the system, and then there's a couple of questions on unit force. So this is probably building on what was taught yesterday in the Intro to Julia course, but you can add two numbers, obviously. And when you do it with uniform quantities, it does what you expect. And of course, you get an error. This is a really nice error to get because you know it's an error. If you just added this without the units, you would get 2, and you would think, great, and then everything subsequently would be wrong. Okay, so then we can create a minimizer. So that's just instantiating this, just constructing the struct, and then we run simulate, and then we run the energy again, and we notice before the energy was 150 kilojoules per mole, and when we minimize it, it's gone down, which is what you'd expect. Okay, so then we can apply random velocities to the system for the Maxwell-Boltzmann distribution, and when we do so, we see that it has standard deviation. I haven't run these in the right order, but you get the idea. So why does the temperature deviate when we call random velocities? So the distribution we're drawing from is Maxwell-Boltzmann distribution. you're basically taking a random Gaussian velocity in each of the 3 dimensions. And so when you generate that for each of the atoms, there will be a slight variation. Okay, hands up who wants me to continue at this point with the answers. 2. Hands up who wants to work on them some more first. Yeah, a couple. Okay, maybe I'll do one more then. So we can plot the energy and temperature. And so when we plot the energy, we see that it's fluctuating around a fairly constant value. So why would we expect this to be fluctuating around a fairly constant value? Not quite, no. It actually relates to your question from earlier about the ensemble we're running in. So here we're just running with a velocity Verlet. Yeah, so there's no thermostat here. So when you run without the thermostat, you run in a constant energy ensemble, okay? So the total energy will be conserved. And we see the temperature fluctuates. And so we could also simulate an MVT ensemble using a Langevin integrator. So here we're keeping the temperature constant. So if we do the same thing, now we see the energy bounces around a lot more because it's no longer conserved. Okay, because the Langevin integrator is adding in noise. Whereas the temperature, okay, the temperature does fluctuate, and this is quite a lot of fluctuation because it's a small system. In a larger system, it would still fluctuate, but that's because it's the mean temperature that's conserved. Okay, in the MVT ensemble, you see the mean is roughly 300. Okay, great. So just carry on working through. I'll come around and feel free to ask me other questions as well.
Doesn't go to 0. It's like standard, like notice you deal with energies.
So you can use non-molar energies, but it just has to be set up with a non-molar contributions to work. Basically, in the code, there's all these hacks.
Yeah, if you have the logger, you have to update the units.
Yeah.
It's just, you have to update the logger units, that's like type of 1 EV. Because by default, I think it's kilojoules per mole.
It's probably
So there's an extra.
That's
going in.
There's a lot of hacks in the code in order to try and get around that molar problem because it is a problem.
It might be actually better to have it like default as dimensions of energy, and then if you want to pull on, then you can transfer to that. Probably easier to do it that way.
Yeah, it's kind of biophysics communities versus, I guess, the FT community. Like, so
Yeah, but like
everyone in biophysics either uses KG or KCal.
yeah, I know, but like it's kind of like because it has the.
I mean, I don't know, I'm not as familiar with the basic stuff for MB.
No, it's still fine. You just need to be consistent with everything else.
Yeah.
So it just means you need to make sure everything else in the system is also molar. So, for instance, the mass has to be gram per mole.
Yeah, so it's.
So that's what makes it
I mean,
consistent.
it varies.
Actually, in unit form, so U,
It's G-pod.
not molar. G per mole is molar.
I've heard it
have to cheaper more.
So we were also wondering with the NVE, like, is this sufficiently stable? I mean, I
Probably
was,
not, no.
I was still surprised by
Yeah,
how
yeah.
much.
Again, I'm playing fast and loose with everything else.
Yeah.
I think it's probably because when it's either too much, time step might be too large or something.
At times, yeah, I think that would be.
That's probably.
But if,
And they actually, like, exact group action.
and you're using a ward, you should be using half X. I think I'm using a one, I can't remember.
That's probably.
I hope with the way that a lot of this stuff is being set up visually is that it's like through the use of like interfaces and stuff, hopefully it can be sort of lightweight, but it's easier.
But does it continue system like
Oh, yeah.
explode?
Oh yeah, it's 5 times a second. So yeah, you.
Oh,
you're
5
quite-
times. Yeah,
It's like
there should be actually.
Oh no, I'm wrong.
Oh, it's half.
something's weird about it.
I was being optimistic.
Yeah.
So, yeah, I mean, it is surprising. I mean, you were saying that like the cutoff.
Yes, like the way how it handles the cutoff. So if it's not going
Yeah,
to
yeah,
zero
yeah,
at
so
the
this-
cutoff, then you can see.
So yeah, so we do have functions for that, we're just not using them.
Oh, yeah.
Because as a molecule crosses the cutoff, it's going to be introducing a finite amount of energy. To smooth it.
Is this what the time file is supposed to look like?
Yeah.
Yeah.
So if you search Ramachandran on Google, you can see
The function that has the right inputs.
the helices.
Okay, so it is expected that it's that.
Still running those stuff. So this is a project showing the basic.
Yeah, so this is one of the annoying complexities of the units thing. You have to have a
What is this dimensions here?
off the top of my head.
Okay.
Let me just check.
And then it converts internally.
So basically, it creates an array of that type to store it.
Without the
So every step is trying to add one EV. The problem is before it's trying to add one EV into an array which is a type.
But why are they dimensionally coded?
All the things that you.
Motor and unit. It's a dimension of number. It's n.
Just returns this sort of modified.
If you call dimension of gram per mole, it's m over n.
So you see that you have everything that's so
Because so in SI units, mole is in
that's a convention.
it's treated as having a dimension.
That's the issue.
What is the best practice within this environment if you want to start a trajectory again?
So like I don't know how far you've gone through that exercise, but have the notebook open, you can actually just see, I mean, he shows it for like energy and temperature.
Okay.
And you can write your own too, which is, he shows an example of that in the notebook as well. So if you go back to the notebook, maybe. Or later on. Yeah, really. There's like a values function you call. also some, I don't know, maybe this is not the question you're asking, but there's also some like clever stuff you can do with callbacks, so. You don't have to like recalculate that, there's ways you can like plug in to grab that from the potential calculation and like feed it right out. I'm not sure if that's the question you're asking, but.
Oh, okay, that's quite.
Yeah, that's a good function.
But in all this, headers, the last line is just this call to run orders, and you give it the system neighbor list. This is just a flag saying if you run one. Okay, whatever property you want.
Right, so what's happening there is you're using the same.
There was a point when I was gonna try. There's still an issue open, because right now interactions don't take velocity. So it's like, why the hell did you do that? But I was the one who originally asked us the question, and the issue is actually still open. That's the problem, API changes.
Oh, yeah, so.
Allow them to input like more generic stuff.
Yeah,
We'll
you
get
have
into
to.
that.
No, but it would be a breaking syntax change. I think.
It'd be a bad addition, it's not just for, also for
No.
dynamics.
Right. There's other things you might want to learn. That was the thing that got me stuck at the time when I was gonna try to, the clever package name and everything was gonna be called Molly model. That's really the most important thing.
That's a good name.
Have a winning name for your package.
It's hard to come up with that. I'm just search Molly, it just comes up with that, I'm like, oh, I guess I need to put Julie.
There's still some, we'll discuss it in a bit, why there's still some.
Yeah, you can simulate a Molly and
So
Molly.
when I added like.
Say Molly and Molly.
Because I didn't have the empty logger with log calculations.
The
There you
force
go.
is like.
That's not a very
You
big
could
market.
calculate the force.
But a lot of these
Force is basically.
Right.
what's the fastest way?
Simulate the
Probably
Just search smiles.
all the energy, so
Just
just
time the library. It'll tell, this is gonna tell you the definition.
every 100 steps. It
I guarantee you that page you had open for MDMA also just has the PG.
You could, what you should do if you were like really.
That's like the least helpful thing I've ever seen. Oh, that's
There's
just
no way this is
lovely.
gonna work. It just gives you a PG.
Yeah, reuse computation, because in this case, you're only doing 100 steps. You
I did this all summer.
Okay.
Nailed it.
But it really thought for a while.
That's really funny.
Yeah, search Peter.
I think it is.
It's definitely on.
So we follow the center. We don't use it.
What the heck?
We do have functions for it. But this Oh, wait. Another particle crossing the boundary.
You are.
Zero jumping.
Yeah, I know, like.
Yeah, it's all there. I found another Easter egg. The mean won't actually be 300. It's something I've brushed.
So does this surprise you? just something just silly.
So the initial configuration.
Yeah,
No, I didn't do something. I just copied this from something.
Python interface. I just wrote a function that goes and comes all the functions that it's really
Velocities,
Oh, yeah.
and the temperature, so it should be the right ones.
It works for rendering stuff, but I couldn't get things to like display beneath.
Well, that's a good question.
so you're recording it
Maybe hundreds.
every 100 steps. So no, that doesn't surprise me because it's quite short. So the mean of that would so in the MVT ensemble, it's the average temperature.
So how many of those installed?
Oh, yeah, okay.
So it's so small that you can get fluctuations that can code off these things.
Oh, good, excellent.
Yeah, I mean, Anderson's like, I don't know, apparently it's like really
Remarkably simple.
love it because it preserves some statistics equilibrium, but to me it's like completely stupid. Like, you randomly just knock an atom. But once with every step,
There's a package
every step knocks.
Yeah, it's I think it's bio.
I think on average it would knock each atom once in 1,000 steps. Yes, use one. So that means
Yeah. So Anderson then picks up the values from the Maxwell distribution every time it's applied. So that's why you get the.
but I doubt it's being applied there because you're running for 1,000 steps with a time step of how much? So you're running for 1 picosecond, so it will experience 1 collision on average during this whole. So it's not basically. So if there's 4 atoms, on average you'll be seeing 4 collisions.
So if I put 10 femtoseconds here, something would happen.
You can try it, yeah.
Yeah, it should then pick up the.
Yeah, it should be more like 300.
I literally just want to make sure it actually runs that allows the entire purpose of this. Very good.
They basically did a wink, wink, nod, nod, so like, yes, that will totally work and you can do it, right?
So we should
Especially after my conversation on this with Justin, where it's like, this actually should be allowed for, especially for faculty, and C just doesn't have the right person. Strings for them. Justin just makes it happen for MSc and Chem. But like, this is also a managed system, but I don't have to, I have pseudo on it. I basically said, I am categorically not spending money on laptop through this mechanism. If I don't have pseudo on it, I can't make install stuff. It's so used to me. The mischief corner over here, they decided to simulate Molly and Molly.
So there we go. So there's.
Yeah.
What does that even mean? Oh, I see. Right.
The
I didn't actually know that was that's not what I called it. I just called it because of molecule. Everyone came up to me and was like, Apparently it's British slang as well. I don't know.
Yeah, they find potentially just in America.
Yeah.
Small molecule would be good for an example.
They have to talk to you.
Yeah.
You can just call it MJ.
We were talking about the rendering.
Yeah. So this one, it just was a library called 3D Model.js, which so this is doing something really stupid. This is literally dumping a massive JavaScript thing into your notebook. So if you save it, you can see that.
It's like HTML.
It's pretty much HTML.
There's something that's glasses.
How can I expose the source of that?
If you just save it and then save the notebook.
If you open it in like, open it in like Emacs or
So
something.
you would see that cell is just like thousands of lines long, and it's because it imports the whole library.
Oh, wow.
Which is
But once you have good
It's kind of amazing it runs that fast.
Yeah.
snapshot.
If you have 5 cells doing that, you have 5 copies of 3D Molly.jl stored.
I said, and the
That's what the story is. JavaScript does that.
Let's put it this way.
Computer lets you then arbitrary HTML. So you can put JavaScript.
Box, just see what happens.
Which is why you're not supposed to run a notebook that someone you don't trust sent you.
I may say, okay, why not try? I don't know that it will be much better.
I mean, there are definitely tools for turning notebooks into relatively nice looking websites, so in that sense, sort of. But it's usually for the purposes of like writing documentation or something where you kind of want the like code and outputs in line, and so that's actually kind of a helpful format.
This is actually the first thing you learn is that you can get 95.
I'm pretty sure that is a thing you can do.
That is probably WebGL.
So then I thought, okay, this is a sleeping class, just switch to that.
I was trying to get it. How to get the interactive thing to show up. You could also check out plotted. So that uses WebGL. I think that works.
Yeah, and I think there are Julia findings for it
There
now.
are,
The thing that, the sad thing with Plotly, I used to
So,
do
yeah,
quite a bit in grad school because I would sometimes make 3D visualizations and it's really easy to like embed them and drag them around. They used to have a much higher limit of how many you could have on the free account. And now they've turned it down quite a bit, so you have to go in and like clear out your old plots in the like Plotly website, like quite
I
frequently.
think part of it is that there are older school ways of doing
Correct, in the free account, unless you pay for it, then it's like whatever, but at least the last time I looked at this, which was not super recently, but I think it was within the last year, like it became a lot less useful in that respect because you had to do that so often. Every time you would like plot something new, it would create a new thing inside this whole interface. So easily, when you're just iterating on something, you could do it like dozens of times.
for us was
I mean, I guess it's another way to push you to pay for it even more annoyingly, like, no, we're not even gonna do this for you, it's gonna just stop working and then you need to do that yourself, or give us money.
Is it that much better than that plot tracking?
It's, at least at the time when I was using it relatively actively, which was probably like, it was by far the easiest way to like, in a very low effort way, get inside of a notebook, a 3D thing that you could drag around and also have like, so what I was using it for was this was like a materials screening type of project, so I was pulling a ton of stuff from the materials project. And what I really wanted was like, for example, a 3D scatter plot where I could like mouse over a point and get like the materials project index so I could go and look at what it actually was. And so getting those little like pop-up tooltip type things inside of all of this other stuff, like by far it was the easiest way to do that.
actually something that would be cool. Manually
Just because you're trying to keep things in notebooks, they need to
database.
have an account.
Good question. I don't, like I said, I have not used it regularly since quite a while ago, so it's also possible that some of that stuff has changed. And I also don't use notebooks for my own personal like sandboxing nearly as much as I used to. So a lot about my workflow has changed, and probably a lot about how their whole thing works has also changed. So that's just based on my own recollections from, yeah, like probably 6 years ago at this point.
I was using Plotly recently just for some personal stuff, and I never, they keep trying to sell you something, but I never made an account or did anything
Interesting.
like that.
Oh, okay.
It's working fine.
That's good. But yeah, I mean, again, possible something's changed, possible it was something specific about the notebook bit, I'm not sure.
I agree, it's so much easier.
20 MEV, some years from
Okay, guys, we'll just review a few more questions. So we had some interesting discussion about the NVE simulation. So why, if the energy is supposed to be conserved, is the energy not actually conserved? It's just like a bit conserved. That's a very good question. So there's a couple of reasons why that could be. One is time step could be too small, too high. in this case, we're actually using a half femtosecond time step, so it's probably sufficient. However, we are using distance cutoff for the interactions, and we're not using smooth cutoff. We're not using a smooth kind of transition at the boundary. That is available in Molly, we're just not using it here. And so if you imagine, if you have particle I and j, as particle j crosses the boundary of the cutoff, there's a non-zero shift in energy at that moment. So that's probably what's causing the slight deviations in energy. Second thing was about units. So you can use this dimension function, which tells you the dimension of something. So for instance, the dimension of 1 gram is m, which is mass. You'll notice this is a special m. It's like a special character. Similarly, grams times second is mass times time. In Molly, the energy by default is given in kilojoules per mole, which differs from kilojoules by the addition of per mole, and you see that this actually changes the dimension because in unit full, molar is considered a dimension. It's the dimension of number, if you like. So that's a bit hard to get your head around, but if you don't like it, take it up with SI units or whatever. That's their thing. Okay, so if we go on a little bit, so now we're logging these torsion values, and when you plot them, you should get something that looks roughly like this. And if we search the Ramachandran plot, we see that the region here corresponds to the alpha helix, and the region up here corresponds to the beta sheet. We see that we are sampling both of them, which kind of makes sense because proteins can sample either of these, and this is a very, 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 well, it's not a protein, it's just 2 amino acids. So we can sample both of those spaces. And then we can run again without, we're running without the implicit solvent, so this is now a vacuum simulation. So this isn't really particularly physical, I guess, unless you had a molecule floating through space. And you see that it's a bit more spread out, but it still kind of samples the similar region. Okay, so we can log one of the oxygen-hydrogen distances and run a short simulation. And then when we plot the distance over the course of the simulation, you should see something like this. So this is harmonic, roughly, which shouldn't surprise you because we're using a harmonic bond, okay? But you'll see there is slight differences in the top here because it's not just one molecule floating around, it's also interacting with everything else. So estimate roughly from the plot the time per period. Well, if you measure it with a ruler or something, it's roughly 9 femtoseconds. And then, okay, using the formula for the frequency of a spring, estimate the expected time based on the spring constant. So in this case, we can use unit fill again. So we can write something like this. We've got our constant, spring constant here, and then the mass here, and then we just convert it to a unit that's relevant to us here, picosecond, which gets us the frequency. And then if you invert the frequency, you get the time, the oscillation time, and the oscillation time is about 9 femtoseconds, which matches, right? So this is, you should expect. Now we can set up the same thing but with deuterated water. So instead of hydrogen, you're using heavy hydrogen. Do the plot, and this time it looks more like 13 femtoseconds roughly from the plot. Again, we do the estimation, you get about 13 femtoseconds. So this is really just a sanity check that harmonic bonds do reproduce harmonic behavior. Okay, so now we can look at how the water is distributed around one of the carbonyl oxygens. So we can create a function to log the distances. It could look something like this. There's various different ways you could have done this as well. You could have created an array and pushed to it. You could use broadcasting. Many ways. We run the simulation, and then we plot this. So this is telling us, usually it's normalized slightly differently, but this is, basically you're seeing two peaks here. The first peak you're seeing around 3 angstroms is the first shell of water. Okay, so you have water that kind of interacts at this characteristic distance around this carbonyl atom. And then around 5 angstroms, you see the second shell of water. So this is kind of giving you some indication that water is ordered around this atom. Okay, so I think we will have another 10-15 minutes, and then we'll just go through the last answers. Oh, I see. So yeah, system loggers is actually a function. So it's a container of other loggers. It's a container of other loggers. So okay. It's a name platform. So system loggers.writer is a structure writer. System loggers.file becomes that.
Where are those actually?
So if you do values, then it's system loggers.file.
So basically, this is the distance from the so has to like get from there, right? So it's distance because these are possible pixels. Well, I'm just confused. Why does it need the coordinate J? It's like better.
There are definitely a lot of ways to customize broadcasting, but some of them are probably kind of.
It's pairwise.
So basically you need types.
All right, so let's go over some more and finish off. So, question asks you about the double exponential potential, which is a variant or kind of a proposed displacement to the Lenz's potential. So here's the potential form, and then first you can either do a bit of calculus or just let Wolfram Alpha do some calculus for you, and you would derive the force functions looking fairly similar. It's down there. And then we want to write a custom interaction. So in this case, we want to define a subtype of pairwise interaction, storing alpha and beta. And here I'm also storing the prefactors. You don't have to do that, but these terms here up front will always be the same, so you can pre-compute them if you want for speed. And then we write the potential function and the force function. And the next exercise asks you to basically get some arrays and plot them. And if you plot them with parameters, I suggest that you see that they look very, very similar. Double exponential form is very flexible and can basically fit the Lenz-Jones form more or less. And you can try with different parameters as well and see how they affect the propulsion and traction. Okay, and then final example for now is using measurements.jl, where you propagate uncertainties. So in this case, we can calculate the total energy and see that it varies by quite a lot. So which the kinetic energy and potential energy contributes more? Well, we can just calculate the values and see, okay? So here we see the kinetic energy, not much uncertainty, and the potential energy has much more. And you can think about why, because the potential energy includes harmonic bonds, so slight variations in position will have a large effect there, whereas the kinetic energy is based on the squares of the velocity. So it's a bit more robust to uncertainty. And temperature is also based on the kinetic energy, so it's a bit more robust. And I don't think I'll go over the differentiable examples. If anyone wants to speak to me about those, just grab me at the break or hackathon. Okay, so does anybody have any questions about either the exercises or Molly in general? Okay. I'll just finish off by giving quick ideas for any hackathon projects. If people are interested, then just come grab me to talk about them, whatever. We don't currently write out compressed file formats, so you can write out PDB files, but really if you want to be running longer simulations, you need to output binary formats. So we can use chem files to do that. So that's mainly a wrapper thing. Basically, the code already exists, we just need to wrap it. There are actually examples of running simulations with base potentials. I think Timu has one, but we can do more on that. We can implement more simulators like fire minimization, more barostats. If you want to implement your cool example system and add it to the Molly docs, then absolutely go ahead. We have a big examples page, or just reading and improving the documentation. By the examples page, I mean this page here, which has, I think, more than 10 random examples now, all the way from the solar system thing Rachel mentioned to kind of agent-based modeling, OligoML, so these molecules flopping around, using an ASE calculator for Python, DFTK example we spoke about earlier, integrated with Athens calculators, and then various like plots of comparing potentials, which is quite nice. Using simple crystals from Ethan to set up crystal systems, and then running constraint dynamics. So if you have some cool example, it'd be nice to add it to this page as well. Otherwise, thanks very much again, and yeah, hope you all enjoy the coffee break.